All right. Chapter 3, number 18. I'll label my axes, time and seconds. It doesn't have to be seconds, but we've got enough other things to think about. This is going to be 10 seconds. I think we're using 10.0. I can write the units or not because I've got the units there. I split that in half, make that 5, 2.5, so 2, 3, 1, 2, 3, 4. The beauty of dry erase. 5, 6, 7, 8, 9, 10. I want to make it reasonably clean. I would actually use a ruler. I kind of like doing that sort of stuff. Then I just got 1 and 2 and 1 and 2. All right, cool. Positive velocity means I'm going in the positive direction. Notice this. I'm going to just say this because this is often, again, because it's really lack of familiarity. Here means you're not moving. Velocity 0. Anytime the graph crosses that or stays there, velocity 0. Here means you're traveling, and I think I do have that. I think 1 meter per second. Here, 2 meter per second. This means -1, which means 1 meter per second. Same speed, just the opposite direction. And now faster, not less. On a number line, you know, if you have -$2, that's less than or more debt than -$1. So, but -2 meter per second faster. So you're going faster either way. This one's just in the negative direction. This one's in the positive. So that's really, I would say the #1 training in this course is connecting meaning of process to any of the math. But there's other things too. All right. So I've got this picture. Let's just draw a graph. Go out to, now the reason that I do this little dot, this says I've got no velocity, right? And then all of a sudden I've got velocity. How did that happen? You can't do that. You got to accelerate, you got to increase speed. So a straight line is a fake thing that sometimes you see. It makes things easier to calculate, and then a flat line here, and then I'll just go like this. In reality, there's no sharp corners in physics. And I'll go down 1. And somehow I've gone from going in a plus direction at 1 meter per second. I didn't even stop. I just all of a sudden am going in the negative direction for 3 seconds. And then for 1 second, I go like this. There's something in here I wanted to change. And then out here. So there's my graph. And these sharp corners are idealizations or, well, whatever. You can't, they happen so quickly, you can't really tell. All right, so reading this at T1 is 0 seconds. Now, the one thing I'm working is like reading this carefully. T2 is not 2 seconds. They're different times. So T1, this red is this is state 1, and we know it goes this way, but I'll just number it 1. An object position is at 1.0 meters. So I'm going to do T1 is 0.0 seconds. Position X1 is at 1.0 meter. I might make a plus just to make sure I don't mess that up. And moves in a way reflected by the graph. The states of interest are, well, T1, I should say, and T2 is 4 seconds. 1, 2, 3. So that's another state, which is going to be up here and here, which is an interesting thing. How can you have both of those velocities at once? You can't. That's an idealization that I want to bring out. 7 seconds, so that's state 2, and then 4, 5, 6, 7, state 3. 8 seconds, state 4, and 10 seconds, state 5, which on the graph is here, there, and that's a funny thing on purpose. I'm not sure. I left out some of the subtlety. Okay, cool. So I've laid out my puzzle pieces. Use the graph to calculate the answers. Write your steps on paper. Trust me on that. Okay. What's the displacement from 1 to 2? Knowing this, what's x2? Okay, I can get this 2 ways. I think the first thing to do is look, I'm looking at a velocity versus time. So I've got points on the graph, which is certain a velocity at a time. I've got slope of the graph, which is going to be acceleration, average, which is change in velocity over change in t. Change in this over change in that. And then I've got graphical area. Really think it's a good idea, good practice to say graphical area, which would be this times the change in that, a change in t. I'm going to go goes like, because it might be the triangle of a half. And that's going to be up, 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 up. See? Talking and writing.
Oh, I was wondering.
Yeah, good.
I
And
crossed my notes. I thought you were.
oh, yeah.
Okay.
All right, cool. So I can, from this graph, I can look at the velocity, I can look at the average acceleration, and I can see the displacement. I can't see the position, but
Right.
that's why I gave it to you. So that means I'm looking for area. Okay, so there's 2 ways to answer this, from 1 to 2. Okay, I know from here, you're not moving. So from 0 seconds to 2 seconds, you're going to still be at that same place. But I'm asked what's the displacement? So I'm going to write this. I'm going to go. I want the displacement from state 1 to state 2, not time 2. And then knowing this, because I looked at that graph, that's going to be, oh, it's going to be the graphical area, 1 to 2. And then I go, I got no area here, but I do have this area, which is going to be 1.0 meters per second. So I'm going to have positive 1.0 meters per second over 2 seconds. And so my change is going to be meters per second times seconds, going to give me my meters. So that's all cool. A positive 2. But I started at 1. So in my head, I can go, oh, then I'm at 3. Or I could do this. I could say x2 minus x1. That's what the change is. So many ways to write this. And again, it's such a language thing. So x2 is x1 plus the change, in this case 2.0 meters, which is 1.0 meters plus 2.0, just to be really thing. And then x2 is equal to 3.0 meters. Bam. x2 is plus 3.0 meters. Good so far?
Actually, let me just make sure. Can you graphically show where you were taking the areas from for both those two?
Yeah. So I'm just going 1 to 2 is here.
Yes.
I've got no area here. So
I see.
I've only got this area
Oh, because there's no acceleration at that point.
or no velocity.
No velocity. Oh, no velocity. Got
Also
it.
no acceleration, but yeah. And then somehow I magically have speed and direction. Somehow I magically have velocity instantly, which doesn't happen. And then, but it could be pretty fast, but still. So I calculate that area as 1 times 1, 2 seconds. That would be my delta t, 2 seconds. It's a rectangle, so 1 times 2.
That's 2 meters.
Yeah, that's the 2 meters. But this is delta x is also delta anything is the later minus the earlier. So I could either say to myself, look, the change is 2. I started at 1, so I'm at 3. It's good to be able to do it both ways. My displacement was +2. I started at 1, so I'm going to be at 3. Or writing it out when it gets more complicated. This is good to practice for that. x2 minus x1 is 2. Add that to both sides. x2 is x1 plus 2. x1 is 1.02. And then I'd feel pretty confident there. Does that look good?
Yes.
And then I could do the same. Then I go, what's not realistic? Yeah.
I think we were saying the same thing.
Yeah, so velocity is constant here, and then magically it goes to here and it's constant. Notice the slope is 0. That tells me what? If the slope on this graph is 0, what does that tell me?
That's what it sounds. It's a rectangle, right?
Yeah, it does. It does tell me that. Yeah.
Oh.
What else does it tell me? What does slope on this graph tell me? Delta V over delta T.
Acceleration.
Yeah. And so there's multiple ways of saying the same thing. You can see on the graph, the velocity is not changing. It could be 0 or it could be something else or here. But if it's not changing, you see that as a 0 slope. And that is the acceleration. So you see it multiple ways, and people that have used this see all of that. Now, part 2, what's not realistic about graph at 2 and at 3. At 2, somehow, at that instant, this object has positive 1 meter per second and then negative 1 meter per second. That's not realistic. That's one thing.
I have to do making sure I really get this part. The first part, how you get x2, is it regular graphical area? Multiplying the height.
Wait, I think I'm not quite.
Oh, sorry. I just want to make sure I know how you got x2. You multiplied, did you do the rectangular graphical area? So you did the height times the base?
No, so x2 I got because I already did, the graphical area was done here. Let me do this. That's the graphical area.
Right.
Then
That's
the-
what that was. That was the height times the base.
Yeah, so that's plus 2.0 meters. That times that.
Okay.
And this is 2 seconds, 2.0 seconds.
Okay.
And then I said, well, wait a minute, X change in anything is later minus earlier.
Okay.
And I know this one was X1, but I could just do the math, add that to both sides, and that's X1 plus my initial position plus the change. 1 plus 2 giving me the 3 meters.
Oh, I'm not sure I understand that part. Why did you add another one to the area?
I did it. I didn't add, so the area is 2. Let me do it this way. Sorry. So we're getting, yeah, it can seem circular, and so we don't want to go in a circle. X2 minus X1 is by definition delta X1 to 2.
Right.
On a graph, on this graph, I get that with the area.
Uh-huh.
Now, mathematically, I could add X1 to both sides. So I could move this around, and you're going to do this in the next chapter. That's so thinking in words, my position at state 2 is my position at state 1 plus the displacement. But I got this here from the rectangle.
Yeah.
This I had to give you.
Uh-huh.
So that was 1.0 meter plus 2.0 meter.
Okay.
So I'm using I'm finding delta, I'm writing delta X 2 ways. One as the graphical area that gave it to me. And then I have to go, well, that's your displacement. Where did you start? Oh, so you got to add that to where I started. The 2.
Okay.
And that does give people trouble. Does that make sense?
Yeah, sort of.
Yes.
Yeah.
That gives
Yeah. It's tricky though, right? And so people that might be listening to this that teach it should take heed to realize that it's just a familiarity thing that lets you just throw this around so fast. I mean, you have to stopping and thinking about it is you gotta, there's a lot going on here in your brain with new stuff.
Hmm.
So that's
I guess it's really, I feel like it really throws me off that the graph itself doesn't show those positions. And so I'm still like looking at it, hoping to see where the position goes.
right. And it doesn't. And that's
You
the
know?
important thing is like, you can't tell a position here. In fact,
I know.
we do this lab in our physics classes for this, where we have you try to walk according to this graph basically. And there's a motion detector. It sends out a sound wave and bounces off of you. So it tells you where you are and how fast you're going. And so you have to walk and try to keep a constant velocity, which is hard because your steps, your body is going like this. So it's all jagged. And then you're supposed to, well, we have it actually, you stop and you sit there and then you go the other way. But we set it up so you go the back. Here you're going away from the detector. You stop and then you go toward the detector, but we have you go toward the detector for a longer time. And if people started at the detector, they run into it. So we set them up and they go, why? Because it doesn't tell you where to start. So you could start out here and then you would have plenty of room to keep going. Doesn't tell you where to start. So yeah, what a graph tells you and what a graph doesn't tell you.
I gotta feel satisfied because I can't see it, you know?
Yeah. And this though is why I, again, I think it's pretty, this stuff it's profound. We're taking imagining a process, doing it in graphs, reading the graph, and then doing it in algebraic, beginning to do the algebra, which is chapter 4 too, moving the symbols around. And the common thing is that people go straight to moving symbols around. Connecting process, graph, and symbols. Whew, that's a lot. If that makes sense. But yeah. But like I said, the good thing is those are your tools for the most part. So whether you learn new physics or not, when you learn new physics, you're still doing the same thing. So you don't have to relearn this. You have to think about new physics, but yeah. So going here. What's not realistic about 2 and 3? So state 2 is here, and that says you got, at that instant, you have both a positive velocity and negative. I mean, I guess I could have with my hands, you know, but, you know, not an object. And the other thing that's not realistic about state 2, what's the slope here? I mean, I've got a change in velocity over 0 time. So something over 0 is undefined or infinite. So somehow you've got an infinite acceleration. That'd be cool.
Why not?
So, you know, and books have gotten a little bit better about this, but for so long they would do these things. And then when you're thinking about it and really trying to learn it, it's frustrating because you're going, what? This doesn't make sense. They still do some things that don't make sense typically, but
So in the real world, there will be another point.
yeah, in reality, it would go like this. That's great. Let me show you. In reality, it would go like, you would have 0 velocity, and then you would eventually build up to a velocity, and then you would go down and then turn around. You would be walking forward, but slower and slower, stop, turn around, walk faster and faster the other way. And then at 3, the same thing. You got a constant velocity with 0 acceleration, and then you've got some acceleration. This would be rounded too. Would ramp. So everything, you can't really have these sharp corners happening, and that gets back at things not being able to change in an instant. They can be changing, but they can't change. And I just let that go. Process that. Displacement from 2 to 3. Boom. Okay. 2 to 3. I got that. So displacement 2 to 3. And you know, of course, why this is nice is it's easy to calculate the area. So given that this is a idealization, then I get that area, but it's negative. So it's going to be negative 1.0 meters per second times 3.0 seconds. And that's going to be my displacement from 2 to 3. And then you want to find x3. So I have you do this because it's an important little thing and it is annoying to people. So I know my displacement's negative 3.0 meters from here to here because you're going backward, negative 1.0 meters per second. Pretty, little bit slow on the walking side, but kind of walking. But I started at 3. So if I start at 3 and then I go backwards 3, I got to be at 0. Once again, I could say that's x3 minus x2 is negative 3.0 meters. If I want to know x3 is equal to add x2 to both sides. I could write it as this, which is x2 is plus 3.0 meters plus x, the displacement was negative 3.0 meters. And I get the answer that makes sense. And so the position x3 is 0. So the area is given the, like you said, the area is given the displacement, but not the position. But if I know the position, I can work it out with a little bit of algebra. So moving that stuff around, like I say, is what you're really heading right into. And that's, you know, by design to move you into the chapter 4 and moving this stuff around like crazy. And really being displacement from 3 to 4. That's a triangle. So half of this times that. And it's going to be a negative. Displacement 4 to 5. I'm not sure if there's an answer wrong in this one. I think answers might be wrong. And you keep doing it all the way through, same way. So then I ask you to describe all these sections, you know. Zero velocity, magically, 1.0 meter per second in the positive direction, magically negative 1.0 meter per second, and then negative the other way. And then going negative, I'm still traveling negative. I still got a negative displacement. This one's really an interesting and important one.
Before you get into that, in terms of you're saying displacement from 3 to 4 is going to be a triangle.
Oh, yeah, I'm not getting you.
You're saying displacement from 3 to 4 is going to be a triangle area?
Yeah,
I just want to see what that is because I see 3 to 4 on the same line.
sure. And again, I might have an error. I'm not sure, but let's see it. And the reason. So this is a really, you know, again, high level.
I think I understand that.
Because if you kept this same speed in the negative direction, you would travel farther. But what you're actually doing is you're starting out at that speed, but you're going slower and slower. Still, if say that's the negative direction, you're still, you know, you're going negative 1.0 meters per second, 1.0 meter per second, say negative, but you're going slower and slower, still negative, but slowing down. You're not going in the positive direction at all. And then you stop right there. Slow down, stop, V4 equals 0. And then you start going faster and faster in the positive direction. And so here, you're not going to travel as far because you're going slower and slower and slower and slower. If you kept that speed, you would have traveled farther. More area, plus here you're decreasing speed. You're not going to travel as far. That's physical thinking. Graphical thinking, if I kept that speed, I'd have more area on a V versus T. The physical visualizing is the motion, the motion diagrams. Connecting that with this. You really don't want to be doing that while you're taking the class. Say 3 to 4. Now, if I had X4 and X3, I just calculated it that way. But I have a graph, so I'm going to do the graphical area 3 to 4 on a V versus T. In that case, it's going to be half negative 1.0 meter per second over 1.0 seconds which is negative, and I would write it as a decimal point. Check my solution because I don't know. I think I might have something wrong. I'm not sure if I have anything wrong in there. But you could go from 3 to 5, and then you just have a negative area, and then you have this positive area. If I go 3 to 5, it's still the graphical area from now 3 to 5. And then you just look at it. And the other way is if you've got an equation for the curves, you can integrate with calculus. Computers can do it for you. Whatever that is, understanding it is really the hard part. I'll tell you, are we good with this?
No, I think yeah, basically. I mean, I'm just kind of trying to catch everything.
Yeah, no, it's, round and round, you get, but I'll tell you, I think this is pretty cool. I am happy that I'm not old enough to have done it, but I was told of this, and it apparently was real. Even in industry, you've got graphs, and the way they used to, everything was so much slower, the way they plot things out. If they had a piece of paper and they had a graph like this on it, they would literally, so they would take their scale and they would weigh the paper, and then they would cut out the graph and weigh that to see how much paper was in the graph.
Huh.
And from that, they could figure out the area and the value.
Wow.
I think that's pretty darn clever.
Wow.
No, but we've come a little ways from there. But I like seeing that kind of, a little more tangible way of doing it. I think that's useful.
Can you see any work through the rest of the
I can't hear you.
Can you hear me now?
Yeah.
Okay. Can you look through the rest of 18 and 19 and see if there's anything substantially different in terms of what you're having us do?
Yeah.
And then 19 has a different.
No, not really. And
Similar.
it's similar, but then 19, I go acceleration versus time. So then I go up here and I go, oh, that's my points are the acceleration at a time. My slope is change in acceleration over time, which is called jerk, and we're not going to look at that really. But my graphical area is going to be acceleration times time, or change in velocity. And so it's going to be the same kind of math. It's just a little different meaning now with this. I mean, that, like I say, I'm talking.
Go back and figure out the position. We don't have to go back and figure out the position. That would be counting.
No, yeah. You
No,
and see, this is why
there's
you're
one
not,
position. X3. Wait, no, sorry. Go ahead. Sorry.
this is why this puts you in such a good place to do chapter 4, because then you'll see how you do that.
We have so much to look forward to.
All right. Great.
Yeah, so much to look forward to.
Oh,
Oh, that's bad. Oh.
it's so bad I didn't think of it.
But like I say, I mean, I think breaking it down like this, and I'm trying to get some time to share this with some people that teach this, to realize that you guys are sharp folks, and it's not easy. It takes a little bit of time, and so if we can provide a ramp at the front end before getting into the class, won't beat up people, or people won't just fake their way through it.
Yeah, I can't imagine being like 18 and like taking this class and being like, maybe having another physics class at the same time. I would, you know.
Yeah. Yeah. Kind of crazy. So, but you
Although
guys
it
are,
might be easier if you don't have any responsibilities in your life, but
yeah, yeah, but there's a lot of students that have to carry
they
their
may
own,
have to work a job or something too, right? So yeah,
yeah.
totally.
And they may not have the confidence, too.
Right.
So there's that. And then you feel like, oh, I'm just dumb. I can't do this. And then you see someone else doing it. Well, who knows what their background was, and it doesn't matter. They can do whatever they can do. Your job is to get it and move on and do what you want to do. And so that kind of stuff thwarts really good people. Cool. Thank you, guys.
Thank you.
John, if you want to make a note, there's an answer.
Oh,
I think in the wrong unit.
Oh yeah, 18. Yes, 18 number 4.
Oh,
Yes, 18 number
hold on.
uh-oh.
3
Hold
to
on.
4. Yeah, 18 number 4 should be 1.0 seconds, not 2.0. Good, thanks. I knew there was something, but that piece of paper got got crumpled. My little note to myself that I had a mistake. Okay, now I got a better marker.
I have
Cool.
a different one. A different one.
Yeah, you
for
found a different one.
Number 13B.
Yeah. 13B.
Yeah, yeah. You were saying miles per hour.
Yeah,
Everywhere.
the units are.
Oh man.
I'm sorry. Sorry, we have to tell you that.
No, talk about details.
Can't imagine writing a book like this.
Yeah,
I think so.
it was a push, but it's a unique thing, and I really wanted to share it, and hopefully people will start implementing it so that our students they can be strong. I'm going to end this, stop this recording.